Hello everyone, welcome back to Statistics. Here is Jonathan. So today we are going to talk about Lecture 5, Random Variables. Let me start by an introduction. So first, again, we have a machine, and let's denote this machine as X, capital X. Suppose that we are doing an experiment, and by doing the experiment we get an outcome. Now, if we take this outcome as an input of X, this machine, and the machine returns a numerical value, that's exactly what a random variable is. Okay, so if you don't understand till now what is a random variable, let's try to do an example. Here is the example. Suppose that we are rolling a die, and let's define X. It returns 0 if the outcome is even, and returns 1 if the outcome is odd. So let's see how it works. So again, let's draw our machine. Here is X. And let's say that we are doing an experiment, rolling a die. So let's do it together. Clack, 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 clack. Suppose that we get 1. So from the experiment, we got 1. Okay, great. So now, by putting the outcome 1 into the machine, according to the definition of X, 1 is an odd number, and therefore X needs to return 1. Let's do another example. Again, I'm rolling the die. Clack, 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 clack. Suppose I get now 2. 2 is an even outcome, and therefore the machine needs to return what? 0. And so on. So for any outcome that we get from the experiment that is even, X, the random variable X, returns 0. If from the experiment we get an outcome that is odd, then in this case, the machine, the random variable X, returns 1. So that's basically what a random variable is. Now that we understood what a random variable is, let me write the definition. Here's the definition. Okay, so a random variable X is a function. So how exactly we denote this? As capital X. So now we have to write the domain. Okay, what is the domain? I mean, where the inputs comes from. So we said that the inputs comes from the experiment. So what are the different outcomes of the experiment? How exactly we denoted all the outcomes of the experiment? Let me remind you, that's exactly the sample space. And then, after putting the outcome from the experiment, that returns a numerical value. So numerical value we denote as R. R represent real numbers. Any numbers that you can think about. Okay, now here's the notation. In the previous example, I used X, but we can use other letters, other capital letters. X, it can be Y, it can be Z, and so on. It can be any capital letters that you want. Okay, so basically we're going to use X, Y, and Z. It can be also S, any letter that you choose. Okay, now let me do a more complicated example. Okay, suppose now that we are tossing 3 coins, one after the other, and we define X to be the number of tails in the experiment. Okay, great. Now, before we start and try to understand what X returns, let's try to understand how the sample space looks like. So what do we add in the sample space? What are the different outcomes that we can get from the experiment? So let me start. So it's adds. It can be adds, tails, or maybe adds, tails, heads, or maybe tails, heads. Now we can add one more tail. So suppose that it's add, tails, and then it can be also tails, heads, tails. It can be also tails, heads, and last one, heads, tails, and tails. So how many do we have here? How many outcomes in the sample space? Another way to ask it, what is the cardinality of the sample space? So if you count them, 1, 2, 3, 4, 5, 6, 7, 8. So in total you have 8 different outcomes. By the way, there is a way to compute those 8 without writing them explicitly if someone knows a bit combinatorics. So you have every time 2 options, or adds or tails. So 2 times 2 times 2, in the end, you'll get 8. Okay. Anyway, it's not important now, okay? Now I'd like to understand what X equals to 0 means. X equals to 0 means that we didn't get any tails. So that means that the only option is that we get only S. Okay. What about X equals to 1? X equals to 1 means that we got exactly 1 tail. Exactly 1 tail. So let's see here, 1, 2, and 3. Okay, so those are the only 3 options. Let's write them. So it can be heads, tail, or heads, tail, heads, or tails, heads. In total, 3 options. Okay. What about X equals to 2? X equals to 2 means that we have exactly 2 tails. Exactly 2 tails. Those are the only 3 options. Let's write them. So it's heads, tails, or tails, heads, tail, or tails, heads. Great. What about X equals to 3? X equals to 3 means that we have exactly 3 tails. Exactly 3 tails means that there is only one option, the last one. Tails, and tails. So here, the outcome for X equals to 3. So if you think about it, we covered all the different options. And from here, we understand that the only values, numerical values, that X can return is 0, 1, 2, and 3. And the way to denote it is writing that X of omega, that's all 0, or 1, or 2, or 3. Again, What do we mean by x omega equals to 0, 1, 2, 3? That's exactly the values that x returns. So for example, again, if you are doing the experiment, in this case tossing 3 coins, and you get heads, heads, tails, then x returns 1. If you get tails, tails, x returns 3, and so on. Okay? But in general, the only values that x can return is 0, 1, 2, or 3. Now, I'd like to talk about computing probability of random variables. Suppose that I ask you, what is the probability that x equals to 0? Asking what is the probability that x equals to 0, that's equivalent to asking the question, what is the probability that we get heads, heads, heads? So we can write that. What is the probability that we get heads, heads, and again, heads? Now, if you think about it, that's one option out of 8. It's a uniform sample space, and therefore the probability is 1 over 8. Let's do the same for x equals to 1. Suppose that I ask you, what is the probability that x equals to 1? So there are 3 options out of 8. So that's the probability that we get head, tails, head, or tails, head. So again, 3 options out of 8. So 3 over 8. And you can do the same for x equals to 2. You'll get exactly 3 over 8. And x equals to 3, 1 over 8. So now we have the different values of x. We have the probability to get each of those values. We can summarize it by using a table. Let's do that. Okay. First, we are going to write the different values that x can return. So we said that it's 0, or 1, or 2, or 3. Next, in the second row, we are going to write the probability to get each of those x. So for example, here we are going to write what is the probability that x equals to 0. Here we are going to write the probability that x equals to 1, and so on. So we already computed those probability. For 0, we get 1 over 8. For 1, we get 3 over 8, 3 over 8, and then 1 over 8. Please notice that in the end, if you sum up those probability, you must get 1. And intuitively, you need to understand that we must get 1. Why? Because in the end, that covers all the different possibilities, meaning all the different outcomes of the sample space. And we know that the probability of the sample space equal to xm2, that's exactly 1. So intuitively, we need to understand that when you sum all the probabilities, you must get 1. Now, this table is what we also call the probability function of x. So let's continue with another example, rolling 2 dice. Suppose that now I define S to be the sum of the 2 outcomes. Before I start, let me try to explain what I mean by that. So, for example, suppose that here is S, and now we are rolling 2 dice. So let's do it, black, 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 black. Suppose that I get first 1. Suppose that I then again roll the second die, black, 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 and then I get 5. So here's the outcome from the experiment. The experiment, let me remind you that that's rolling 2 dice. So now here I got 1 and 5. That's the input. Then S needs to return 1 plus 5, meaning 6. So that's how S is defined. Now here I wrote the sample space of the experiment, meaning all the outcomes that we can get from the experiment, rolling 2 dice. Now I'd like to write the probability function of S. So let me draw the table. Okay, so here is, we need to write, in the first row, we need to write all the different values that S can return. And second one, here we need to write the different probability. So now what are the different values that S can return? So let's see. So by looking at the sample space, we see that the minimum value that S can return needs to be 2. Okay, because here, the worst case scenario, if you think about it, is that getting 1 and 1. 1 plus 1, that's 2. So the minimum is 2. What is the maximum? Okay, the best case scenario, if you want to think about it like that. So it's 6 and 6, meaning 12. Okay, and we can get any value between 2 to 12. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Now we need to understand what is the probability to get each of those values. And here I'd like to show you kind of a magic. Okay, let's see. 2 we can get only if we get 1 and 1. What is the cardinality of omega? How many outcomes do we have in omega? So it's 6 times 6. 6 times 6, of course, 36. So again, the only option to get 2 and 2 is 1 and 1. So it's 1 outcome out of 36. Please remember that rolling 2 dice, that's an experiment that corresponds to a uniform sample space. And therefore, the probability to get S equals to 2, that's exactly 1 over 36. Okay, so that's basically the only option. Now, 3. What are the different possibilities to get 3? So there are only 2, 1 and 2, or 2 and 1. So 2 out of 36, that's exactly the probability to get 3. Now, if you see, I hope that you noticed here that in the end, if I want to get 4, 5, and so on, that's exactly the diagonals. Okay, so for example, for 4, in order to get 4, the only options are those 3 here. So that's going to be exactly 3 over 36, and so on. So 4 over 36, then 5 over 36, 6 over 36. But then, if you draw those diagonals, you'll notice that that's 4 over 36, that's 5 over 36, that's 6 over 36, and then again that becomes 5 over 36, and so on. That's a symmetric property here. So in the end, we get 5 over 36, 4 over 36, 3 over 36, 2 over 36, and 1 over 36. By the way, if you check, you'll get exactly 1 when you sum those probabilities. Again, here we understand we must get 1 because in the end, we covered all the possibilities of omega. Okay, exactly as the same thing that we do on the previous example. Great. Now I'd like to write and explain two properties of random variables. Okay, so properties of random variables, of the S random variables. Okay, one is that the probability of x getting a value, small x, is always non-negative. So I hope it's not a surprise to you, because in the end, we know that probability of any event needs to be non-negative according to axiom 1. Then, second one says that if we sum all the different probabilities over the different values of x, we must get 1 in the end. That's exactly what we explain here. The reason you must get 1 is that we are covering all the sample space. Okay, let's start talking about cumulative distribution function, what we call also CDF. Okay, so what is the definition? The definition says that the cumulative distribution function, denoted as capital F, x that represent the random variable we are talking about, x, small x, that's the probability that x is less than or equals to small x. So first of all, notice that it's called cumulative. Cumulative, it means that we accumulate probabilities. So let's do an example. So one of the examples that we mentioned in class, that's the example of tossing a coin 3 times, and then x represents the number of tails. So x, that's the number of tails. Okay, and then we found the probability function. What was the probability function? So let me remind you. So x returns or 0 or 1 or 2 or 3 tails, and the probability to get each of those values, that was 1 over 8, 3 over 8, 3 over 8, 1 over 8. Okay, now suppose that I ask you not what is the probability that we get exactly 2 tails or 3 tails. I ask you what is the probability that we get at the most 2 tails. That's exactly asking what is the cumulative distribution function when we plug in 2. So what is the probability that x is at most 2? What is the probability that we get at most 2 tails? So that's basically the idea of cumulative distribution function. How exactly we compute that? So saying that the probability is at most 2, that can be or 0, or 1, or 2. And then we sum those probabilities. 1 over 8, plus 3 over 8, plus 3 over 8, 7 over 8. Okay, let's do the same for the CDF at 0. Okay, so what do we get? So saying that we want to compute the cumulative at 0, that's the same as computing the probability such that s is at most 0. Saying that we get at most 0 tails, that's equivalent to saying that we get exactly 0 tails. And the probability that x equals to 0 is 1 over 8. Great. Now what about the cumulative at 1? So that's exactly the same as saying that x is at most 1. But at most 1, that's exactly the same as computing the probability that x is 0 plus the probability that x is 1. So it's 1 over 8 plus 3 over 8, 4 over 8. So the cumulative at 2 we already computed. Let's see what is the cumulative for 3. So before I compute that, think about it. What must be the cumulative at 3? So the cumulative at 3, that's the probability that x is at most 3. Now, it means that we accumulate all the probabilities here. And that must be what? It must be 1. Because we said already that if you accumulate all those probabilities, if you sum those probabilities, you must get 1. Because it covers, again, the sample space. So in the end, that's going to be, of course, 1. Now, let's say that we want to visualize the cumulative distribution. Let's see how we do that. So let's motivate those two. Okay, so let's draw the graph here. Okay, so here the y-axis, here is the x-axis. So here are the different values that x gets. So it can be or 0, or 1, or 2, or 3. Okay, now in general, the cumulative distribution can get any value, not just only 0, 1, 2, or 3, it can get any value. X can be any value, any real value. Okay, so let's see. If I ask you what is the probability that you accumulate up to 0, excluding 0, so up to 0 excluding 0, you didn't accumulate anything. So how do we draw that? So like that, and then we add this empty circle here. Next, if I ask you what is the probability that you accumulate up to 1, excluding 1, okay, without taking into consideration 1, then you accumulate 1 over 8. That's 1 over 8. Now, if I ask you what is the probability that you accumulate up to 2, excluding 2, so up to 2, excluding 2, so that's exactly 4 over 8. Now, the moment that you add 2, okay, that becomes 7 over 8. So what is the probability that you accumulate up to 3, excluding 3? So it's 7 over 8. Let's do it here. And in the end, if I ask you what is the probability that you accumulate up to infinity, including 3, that's going to be 1. Oh, that's 1. That's 7 over 8. And that's how we draw the CDF, the cumulative distribution function. So again, how do we read that? So first, we need to understand that for any value that you're going to give me up to 0, excluding 0, we didn't accumulate anything. That means that the CDF is 0. The moment that you're asking me how much you accumulate up to a value that is between 0 to 1, excluding 1, that's going to be 1 over 8. Between 1 to 2, excluding 2, that's going to be 4 over 8, and so on. So for example, let me just write it. If someone is asking you what is the probability that x is less than or equals to 4, so another way to ask it, what is the CDF at 4? So that means that you want to accumulate all the probabilities up to 4. Up to 4 means that you are here somewhere, and that's exactly 1. Okay, because in the end you accumulate all the probabilities up to 4, meaning you cover all those probabilities, and that needs to be 1. Okay, please notice also that there are two important properties of the CDF. The first property is that the CDF at infinity is 1. So what do we mean by f of infinity? It means that if we take the CDF at a very, very big number, a number that is far, far, far from 3, that means that we accumulate all the probability. So f of infinity must be 1. Now, if I ask you what is the CDF at minus infinity, so that means that we accumulate up to a value that is far on the left side. Okay, and of course, in this case, it means that we accumulate nothing, meaning 0. So those are two properties you should remember. We'll use that later on, but for now, that's all for the CDF. So now let's talk about expected value. So the expected value of a random variable is a weighted average of all possible outcomes. Let's see how we denote that. So the notation is capital E, x, to remind ourselves that we're talking about the expected value of the random variable x. What is the definition? The mathematical definition, of course. So the expected value of x, that's the sum of x times the probability that x equals to x when we go over all the different values of x. I'll show you an example, don't worry. So here's the example. Suppose again, we define x to be the number of tails that we got from tossing 3 coins. Again, same experiment as before, tossing 3 coins. So we already talked about the probability function of x. So let me just remind you, what is the probability function of x? So we can get all 0 or 1 or 2 and 3. The probability to get each of those values, that's 1 over 8, 3 over 8, 3 over 8, and 1 over 8. Okay, now let's compute the expected value of x. How exactly we compute the expected value of x? We take each value multiplied by this probability and then sum them. So it's going to be 0 times 1 over 8, plus 1 times 3 over 8, plus 2 times 3 over 8, plus 3 times 1 over 8. Okay, now what you expect here to get, even if you don't add a calculator, here, I hope, and if not, I'll explain, that you understand that you need to get 1.5. And the reason, the intuition behind it, is that if you look here, we get exactly the same weights for 0, 1, and 2, and 3. Think about probability as weights. 1 over 8, that's exactly the weight on 0. 3 over 8, that's the weight on 1. 3 over 8, that's the weight of 2. And 1 over 8, that's the weight of 3. So now, if you think about it, there is balance here between those two values and those two values. So we expect to get 1.5. That's going to be the expected value of x. Now, let's try to understand what this number means exactly. So that means that this number means that if you repeat infinitely the experiment, so each time you're going to get a value between 0 to 3. So suppose you get 0, then 3, then 1, and you're doing it infinite times. Okay? So on average, you expect to get how many days? 1.5 days. And that's exactly what the expected value represents. So again, 1.5, it means that if you repeat infinite times the experiment, then you expect to get 1.5 days. Okay, so let's solve an example. Rolling 2 dice. So here's the experiment. Now there is a game with different rules. First, if the sum of the outcomes is at least 10 and no doubles, then we win 100 shekels. Second one, if we get doubles, we win 70 shekels. If conditions 1 and 2 holds, we win 170 shekels. Otherwise, we need to pay 25 shekels. So here's the game. Here are the rules. Now we need to figure out if this game is profitable in terms of expected value. So how do we solve those types of questions? First, we need to find the probability function of the game. So let's see. So first, let's draw a table. And let's denote x to be the profit of the game. Now, there are a few possibilities for x. So according to the first rule, we can win 100 shekels. According to the second rule, we can win 70 shekels. And according to rule 3, we can win 170 shekels. Otherwise, we'll need to pay 25 shekels, so minus 25. So those are the possibilities of profit by playing the game. Now let's figure out what is the probability to get each of those numbers. So let's start by the easiest one. Let's start by 70. What exactly? Or even let's start by 100. It's even easier. For example, what exactly we can get 100 shekels? 100 shekels we can get only if the outcome are at least 10 and we don't have any doubles. So here are the possibilities. So it can be 5 or 6, 6 and 5, 4 and 6, or 6 and 4. By the way, what do I mean by doubles? Doubles means 5, 5, 1, 1, and so on. Okay, that's what I mean by doubles. Okay, so now that we know when we can get 100 shekels, when exactly we can get 70? Okay, so 70 we can get only if we get double. Double here it means or 1 and 1, or 2 and 2, or 3 and 3, or 4 and 4. But now be careful. Maybe you ask yourself why we don't need to write here also 5 and 5 and 6 and 6. So let's see, if it's 5 and 5, it means that the sum is at least 10. And also it's a double. And according to rule number 3, we need to get 170 shekels. And therefore, the only options for 170 shekels, that's 5 and 5, and 6 and 6. Okay, great. So what are the different options that we need to write here? All the options that are not part of those options. So everything that is in omega, but not those outcomes. So let's see, now we want to write the probability. So here we wrote the options, but in the end we need to write the probabilities. So here it's 2 over 36. Here it's 4 over 36. Here it's 4 over 36. Now we know that in the end, if we sum all the probabilities, it needs to be 1. So what needs to be this probability? 26 over 36. Okay, so now that we know the exact probability, we need to compute the expected value. So let's do it. For the expected value of x, that's minus 25 times 26 over 36, plus 70 times 4 over 36, plus 100 over times 4 over 36, plus 170 times 2 over 36. And that equals to 10.27. And that's positive. Okay, so again, what this number means, it doesn't mean that if we play one game, we expect to get 10.27. No, of course not. It means that if we play enough times, infinite times, we expect to get a profit of an average of 10.27. So is the game profitable? Yes, the answer is yes, in case that you are playing enough times. So yes, on average, we're going to get a positive profit, and therefore it's profitable. That ends the example. Now I'd like to talk about different properties of the expected value. So one of the most important properties is what we call the linear property. Linear property of the expected value. So what do I mean by linear property? Suppose that I ask you what is the expected value, not of x, but of 2 times x plus a constant, let's say 3. So that's a linear function. Linear function in general, it's the form of ax plus b. Okay, so here we can see that a equals to 2 and b equals to 3. So in this case, we can prove that that equals to 2 times the expected value of x plus 3. Or in general, the formula says that the expected value of a times x plus b, that's the expected value of x times a plus b. So how exactly we can use that? So here's the example from before. Let's assume now that the owner of the game decided to change the rules. And now, instead of talking about those profits, he's going to do something else. He's going to take x, and he's going to multiply it by 2. And let's say, subtract 5. And now, after changing the rules, he's going to ask you, what is the expected value? So suppose that that's what you want to do. So it means that he's going to take each value here, he's going to multiply it by 2, and then subtract 5. Well, let's see, if we are doing that, 2 times minus 25 is minus 50. Minus 5, it's minus 55. So let's see now for 7. 70 times 2, 140, minus 5, 135. 2 times 100 minus 5 is 195. 2 times 170 minus 5, so it's 335. Suppose now that I ask you, what is the expected value of the new probability function? Is it now profitable, yes or not? There are two options. One of them is to compute the expected value from the beginning, meaning taking each value multiplied by its probability, plus the second one times probability, and so on. Another way is to say, okay, so that's a linear function again. And therefore, according to the property that we mentioned before, we can just say that the expected value of 2x minus 5 is exactly 2 times the expected value of x minus 5. And we already computed the expected value of x. Let me remind you that it was 10.27. So what is 2 times 10.27 minus 5? That's exactly 15.54. That's also positive and even bigger than the previous value that we got. So that's a way that we can use this linear property in case that you want to compute the expected value of a linear function. And it's important, only linear function, not quadratic function, only linear function, meaning a times x plus a constant b. Then you can write it like that. Okay, by the way, if b, please notice that if b is 0, so for example, you have ax plus 0, so you don't need to write 0, that's a times the expected value of x. Okay, so that's the first property. The second property that I want you to know is that if you want to compute the expected value of a constant, let's always be a constant. Think about it. The intuition says that, what is the expected value? The expected value, so that's the weighted average. If we repeat on the values of x, if we repeat the same experiment infinite times. So if we repeat the experiment infinite times, here in this case, x is returning always c. So you're going to get c, 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 always c. So on average, what do you expect to get? C. Okay? Another way to understand it is that the expected value of c, that's the same as a random variable defined like that, x. It returns c all the time with probability 1. And now, what is the expected value of x? So the expected value of x is c times 1. That's exactly c. Okay, so two ways to understand the second property. One says that the expected value of a constant, that means that we always get the same constant by doing the experiments. On average, we expect to get c. That's one way to understand it. Another way is to say, okay, so by doing by a constant, we can always define a random variable that returns only c. So that's why it's probability 1. And if we compute the expected value of x, that's going to be c times 1, meaning c. Two ways to understand properties too. Last property is property number 3. Let's do it here. Okay, so property 3 says that if x and y are random variables, then the expected value of the sum of random variables, that's the sum of the expected values. And that ends the 3 properties that we talked about, property number 1, property number 2, and property number 3. See you on the next lecture.